Good afternoon. It's a beautiful day for doing some modern physics. Anyway, this is Chapter 9, Part 8. And so I want to wrap up this section so that I can move on in the next lecture. So we ended with starting to talk about the Stern-Gerlach experiment. And one correction is that I said they sent a beam of sodium ions through a non-uniform magnetic field, and that was incorrect. The S letter's correct, but it's silver. So they sent silver atoms through a non-uniform magnetic field. Now remember, they were looking for evidence of space quantization. And so basically the way this experiment was designed is that, and again, this is looking at it from a side view. So if this is north, this is south. And I guess from a perspective point of view, and then this would look something like so. Okay, something like so. And then the bottom would look like this. So here is this is more pointed. So it's flat. Here's north. Here's south. And so if you were to actually do the calculation, if we call this, and I'll use the same notation that's in your textbook, this is B at Z1, this is the magnetic field at Z2, and here is the Z direction. Okay, likewise here, this would be the Z direction. Then if you were to look at the magnetic field lines, right, then BZ2 is greater than magnetic field at Z1. So if you were actually to send in some magnetic moments, and if this were the magnetic moment mu, then the force on this part, right, is going to be greater than the force on this part. And likewise, if we were to look at a mu in this direction, then the force on this part would be greater than the force on this part. So what we have then is that there's going to be a torque on these mu's to try to align them with the field, but you know that it can't do that. So these these mu's are actually going to precess in the field. And classically, right? Classically, if we were to have a detector downstream here, right? So if this were some detector here, some screen. So this is some detector. And if you read the article from Physics Today, you'll get to realize exactly what that detector was in 1921. So classically, that if there's no space quantization, then what one expects here is to see a sort of smeared out band, right? So this would be a smeared out band that would actually indicate that mu would have any number of orientations as it went through the magnetic field. But what they actually saw on the detector, was that they saw this kind of arrangement where there was a band up top and a band below, and in between was no detection, which meant that as these magnetic moments went through the non-uniform magnetic field, they could only assume two orientations in the magnetic field, hence space quantization. And then when they came out and struck the detector, they did so with just two bands indicating one orientation or the other. So again, right? To think about this, right? Remember what we said in the earlier lecture was it was expected that one would see an odd number of bands, right, corresponding to 2L plus 1 EMS of L values. Okay, but instead, right, they just saw two bands, right, just two bands, which clearly is even. So I had to explain this somehow, right? And so again, going back and by analogy, if there were two L plus 1 values of EMS of L values for the orbital angular momentum, then they postulated then that the spin on the electron then is one half, which would give then 2s plus 1 EMS of S values. And so then 2 times 1/2 plus 1 is 2. Now remember, right? Remember the EMS of L values. The EMS of L values went from negative L plus 1 through 0, L minus 1 plus L. So they went from negative L to positive L in increments of 1, right? 1 h bar. And so actually in increments of 1. Sorry, I take that back, forget the h bar. And so clearly in this case then, m sub s is going to go, m sub s will go from negative 1/2, right, to positive 1/2, okay, because that's an increment of 1. An increment of 1. So that would mean then that, remember what m sub L was, right? M sub L was the z, right? M sub L times h bar represented the z component of the orbital angular momentum. So m sub s then, m sub s would represent the z component of the intrinsic spin angular momentum. And so m sub s could be equal to plus 1/2, or m sub s can be equal to minus 1/2 h bar. Okay? Or sorry, I'm sorry. I'm going to take that back here. Yeah, there we go. All right. Now we're cooking with gas. So s sub z could be equal to plus 1/2 h bar, or negative 1/2 h bar, where m sub s then was equal to plus or minus 1/2. Okay. Good. Okay. Please make note of that. So again, by analogy, the magnitude of s then is going to be equal to the square root of s times s plus 1 times h bar, which would be equal to the square root of 1/2 plus 1 times h bar, which is the square root of 3/4 times h bar. Right, that's an analogy to magnitude of L equals to the square root of L times L plus 1 h bar. And then s sub z, as we said above, was going to be equal to m sub s h bar, where m sub s is equal to plus or minus 1/2. And again, that's an analogy to LZ is equal to m sub L times h bar. Okay, so we could also use by analogy the vector model that we looked at earlier. And so if we have then our vectors of magnitude s, so this is going to be magnitude s, which is equal to the square root of 3/4 h bar, magnitude s, which is equal to the square root of 3/4 h bar, and now we have the z component of the angular momentum, and that would be this length here and this length here. And so this would be negative 1/2 h bar. This would be positive 1/2 h bar. And we commonly then call this spin up. Hang on here 1 second. So and spin down. And I want to check this, okay, because that might be opposite, because remember this is the, no, this is good. No, this is okay. Yep, we're good. Yep, this is good. This is the z component of the angular momentum, right? So it's the spin up and spin down, right? Very good. Okay, we're good. We're good. All right, so anyway, where we are then, just to wrap this up, is the magnetic moment. The magnetic moment has two contributions. And so the total magnetic moment is actually the sum of the orbital contribution plus the spin contribution, and that's going to be equal to negative E over 2 m sub E. This will be L plus S, and with our added G factor, okay, where we remember that G sub E is 2.0023. Okay, so again, please remember that the electron is not really spinning at all, okay? And so what's on tap next? We're going to look at section 9.3, which is spin-orbit coupling. Spin-orbit coupling, or what your book calls the spin-orbit interaction. It's more commonly known as spin-orbit coupling. And then we'll cover section 9.4, exchange symmetry. And then we'll conclude with a discussion of 9.6 of section 9.6, which is the periodic table, and we'll omit section 9.5. Okay. All right, very good, folks. Enjoy, and we'll be talking to each other on Wednesday. That is tomorrow. All righty, take care.